Kumar Dhoble, sir. I welcome on behalf of Maharishi Karve Stri Shikshan Sanstha and Cummins College of Engineering for Women. I welcome Dr. Dhoble, sir, for the 6th day. That is the last day of this online faculty development program and the 11th session. I'm very happy to share with you, sir, that since 5 days this FDP has been started. It is we are conducting under AICTE training and learning academy, that is ATAL initiative of AICTE. And the topic for the faculty development program we have chosen is 21st century materials, advancements in technology. In this, in association with the ASM International Pune chapter. So far, the many speakers have come and they have discussed with various topics related to materials like nanomaterials, biomaterials, and then materials required for automotive application. Then high pressure fuel injection systems were discussed by Dr. Mr. Prasant from Cummins India Limited, and many such topics we have covered till now. This is the last day of this topic, this faculty development program. And we have got very good response from the across the, I must say the country as well. Many the participants, they are from mechanical, material, physics background. So this is the, brief intro about our FDP. So dear participants, today we have with us Dr. Ashvinkumar Dhoble, sir. Let me take privilege to introduce Dhoble, sir. Dhoble, sir is currently working in mechanical department, VNIT Nagpur as associate professor. Sir has more than 5 years of research and development experience. He was closely associated with Mahindra company, and there he worked on some of the engine related topics, and that was very appreciated at that time. Sir has a total 22 years of teaching experience, more than 35 journal papers and 17 conference papers have been published by sir in very reputed journals. Many PhD students, sir, have been supervised. So far, 7 PhD students and 30 MTech students, sir has guided. One patent to his name. Many the funded projects from the central agencies, sir, working on. So one of the project currently is working on design and development of heat cooling system for lithium-ion batteries used in electric vehicle. So on behalf of Cummins College, I welcome you, sir. And without wasting time, I request you please start with your topic. The current topic, today's topic for this session is energy storage material and its application. Now up to you, sir.
Thank you. Thank you, Prasanna. Thank you for giving me an opportunity to interact with the participants. So, good afternoon, all. I'm Dr. Ashwin Dhoble, as he has introduced. Now we will directly start with the presentation. So, Prasanna, shall I share the presentation?
Yes, sir. Yes, sir. Please share. I have stopped my presentation. You please share.
Yeah. Is it visible?
No. No, sir.
Let me
You
check.
share.
Yeah, share the screen. I have shared the screen.
Now it's visible.
Now the presentation is visible.
Yes, presentation is visible. Slide mode, please do it.
Yeah,
Sir.
I'll.
Okay. Yes, sir. Fine. Perfect.
Perfect. Okay, fine. So now today we will discuss the energy storage materials and the application. First of all, let me tell you that we'll start with the uh, what is mean by energy, then what is the how you can store the energy, and what are the different techniques and technologies, and the present status of these technologies. So the content will be the first thing, the introduction to the topic. Most of you have attended the previous session, so not much introduction is required as far as the energy storage is concerned. And all of you are, I believe, that you work in the area of materials and energy. So right from the ninth class, everyone knows what is energy and the current problem. So usually energy is a very big topic and it is directly related to our life. So everybody is concerned whether he is from any field. So, and the energy storage is a very, very vast topic. So out of that, I am going to consider very few, you can say, the applications, and we will discuss those applications from the overall viewpoint, not doing any kind of technical analysis as such. That means this presentation will not give you any kind of mathematical treatment. Okay, then we will discuss as a engineer, or as a, you can say, a person who is working in the field of energy, the thermodynamics aspect. These are the basic aspects that we should know when we analyze any kind of system. So from the thermodynamics point of view, only two slides I will be discussing on, and those are the very basic slides, because once we are very, very clear about the storage facts, basically the energy interaction in a system, then the rest of it becomes very easy to understand rest of the things. Then the thermal energy storage system, what are different types of thermal energy storage system. Specifically, this will be related to the storage of thermal energy. There are other sorts of energies like electrical, chemical, mechanical. So we will only discuss about the thermal energy storage system. Then energy storage types, what are the different types of storages. Then brief about various techniques which are used and upcoming techniques, future scope and references. So this is basically the broad outline of the presentation which I'll be doing it today. So first, in introduction, that whatever the photographs which are shown on the slides, they all represent energy. This is basically the atomic structure, then the solar panel, then oil, then batteries. All these things, they are concerned about the human life and as well as nature. So first thing, we know that energy system plays a key role in harvesting energy from various sources and converting it into energy forms required for application in various sectors. That means we use energy in various sectors in our day-to-day life: utility, industry, building, transportation. So no doubt that energy is an integral part of our, you can say, living. And spiritually, if you see that, then they say that the spirit which is there in our body is nothing but the energy. That is the spiritual energy. We always used to refer to that. So energy sources like fossil fuels, uh, all of us know that fossil fuels are used for getting the energy traditionally, because they are the traditional source of energy. They are storable whenever required. Whenever they are not required, you can store the energy or store these fuels. Then other sources such as solar and wind energy need to be harvested when available and stored until needed. All these energies, they are abundantly available in the nature, but the seasonal variation of these two energy everyone is aware of. So in order to store this, we need to have the strong storage, you can say, mechanism. so that whenever we require that, we should be in a position to utilize that. For example, everyone knows that for solar energy, it is available during the daytime, so we need to store it in batteries or some other media so that we can use it whenever it is required. So energy may be converted to stored form in chemical, electrical, kinetic, potential, thermal media. It can be converted for final use directly. See, we want that the conversion of one form of energy to other, and that will happen either by storing it in some other form. That means if you have the energy available in the form of, let us say, chemical, you convert it into electrical energy and store it in battery. If it is available in the form of kinetic energy or potential energy, convert it into the mechanical energy, and then in turn you convert it into electrical energy and then store it in battery. So such kind of conversion is required. For some of the cases, the conversion is possible. For some of the cases, the conversion, direct conversion is not possible. But it is most easy thing to convert is in the form of electrical energy. So that is the convenient way for storing the energy. Now, before we discuss about the conversion of energy and storage of energy, we have to look at the fundamental laws, basically the thermodynamic aspects of the energy. All of you are aware of the thermodynamic aspect of energy? Can you say yes, no? Hello, can you hear me?
Yes, sir. Let me check probably to, yeah, the participant, you can unmute yourself. Earlier the setting, anybody?
Yes, sir.
Yes, sir, it is audible.
Yeah. Very good. So, can you tell me what do you mean by energy?
Simply, we can tell that particular thing, sir. It is having that particular tendency to do the work,
Yeah,
the ability to do that work.
energy is basically, we have studied in the during our school days, that it's a capacity of a body to perform the work or produce changes in the environment. It is the force that drives and enables things to happen. So we say we use energy more frequently. Okay, so when we study basically the conversion of energy, we should know what is exactly energy. So energy is a capacity of a body to perform the work. For example, if we say that he is very energetic person, that means he's very active. He has the capacity to do the work. Now, what are the laws which are related to the energy? Have you studied these laws previously, or by chance you came across such kind of laws?
Yes,
Rather, of thermodynamics, sir.
Yeah. But what are the laws which are concerned with the energy?
it is the first law of thermodynamics, sir.
Very good. What it says, ma'am?
Energy can neither create it nor destroy it. It can only store in from one form to the other form,
Yeah.
transfer to the one form.
Yeah. Rather than it can be converted. Instead of storing, it can be converted from one form to another. That means this law only gives us the idea. What do you mean by the law, by the way? Why it is not called as the theorem? Any idea?
Yes, theorem means the terms which we can prove in that particular way.
Yes,
That is
very,
the
very correct.
rather the law. It can be little bit flexible or feasible to turn out in the concepts.
Yeah. Definitely, a law is basically, these are the observed facts in nature. Okay, that means no, you might not, whatever law statement is given, we follow as it is. We don't question that how it is true and all. because this is based on the fact. You will not get any proof in the book that the first proof of the first law of thermodynamics. No, you won't get. It is basically, these are the facts which are observed in nature, and the first law of thermodynamics is law of conservation of energy also. So when we study the energy storage, we should know the basic thing, that energy will remain constant, only it can be converted from one form to other form. And then there were, how many laws of thermodynamics are there?
4.
Okay, very good.
Including zeroth law.
Zeroth law, first, second, and third.
Third.
So the second law everyone knows. It is impossible to devise a heat engine that takes heat from hot reservoir and converts all the energy into useful external work without losing heat to the cold reservoir. See, I'm discussing this in brief because once we understand, then that will form the basis of the losses which are there in the energy storages. So all of you are familiar with this second law of thermodynamics?
Yes, sir.
Yeah. Those who are not familiar, for them, let me explain this thing in brief. That means, if you see in this figure, there are two reservoirs. One is hot and one is cold. Usually the cold reservoir is, you can say, the environment where we reject the heat, and hot reservoir is any infinite temperature source or heat source which is at a higher temperature compared to the ambient temperature. So in between, you set up any of the engine which is working between these two reservoirs, then it says that such kind of situation on the right side, such kind of situation cannot happen. That means you cannot completely convert heat into work. That is what it says. This is by law. And that means some amount of heat has to be rejected to the environment. So understand that if you want to store the energy in any of the media, then some amount of heat in any form should get rejected. That means you cannot store 100% of the heat. So losses are bound to be there, whether we like it or not. Otherwise, it will be an engine working with only one reservoir, which is a violation of the second law of thermodynamics. So please try to understand that whenever we want to store the energy, some amount of heat, or some amount of energy has to be dissipated. So that is the meaning. Now, energy storage system. So here, the basic system is in a pump hydro storage. It is the pump storage electricity is a method of storing and producing electricity to supply high peak demands by pumping water from lower reservoir to an upper reservoir. So if you see this kind of system, it is basically, you have got the lower basin, then turbine, or there will be a pump which you can already store the water at the higher basin. That means you are basically increasing the potential energy of the water. So this is the potential energy of the water. Now whenever it is required, you can allow this to get back to the pump. Now the pump will become a turbine. Turbine is basically producing the energy and you can supply it. So when the power demand is high, water flows from the upper reservoir to lower reservoir, activating the turbines to generate the electricity. Basically, this turbine is connected to the generator to get the electricity. So this is the simplest to understand. So, but this suffers with certain kind of drawbacks that we will see. The first advantage is this is very, very fast responsive. That means whenever you require the energy, you can start this particular system and can get the energy. That means here you store the energy in the form of water. Okay, so water is become the storage media for this kind of system. So this is the advantage of this pump hydro storage, and the major drawback is lies in the scarcity of the available sites for the two large reservoirs and a long lead time around 10 years. That means if you want to build such kind of system, so it is going to take a lot of time. And the literature says that, since I do not work in this particular field, so most of the presentation things I have taken it from the literature, some of the research papers which discuss about such kind of energy storage system. So it says that a long lead time, typically around 10 years, is required for such kind of system. This is basically, you can say that you can store the energy in the form of the water, that is potential energy, convert that into the mechanical energy with the help of the turbine, and then convert that mechanical energy into electrical energy. So if you say that there is going to be losses here, that is first thing, the losses in this section, then losses when you when you generate the electricity and for the transmission and distribution, which you people are very much aware of this. So this is basically the most simple energy storage system for the understanding. The second in this is basically the flywheel energy system, and most of the time it is used for storing the energy. uh, Flywheel is similar to your capacitor in electrical circuit. So in mechanical engineering, most of the systems they use flywheel. For example, internal combustion engines, they use the flywheel. Then in punching operation, they use the bigger flywheel for storing of the energy, and then they take out the energy from the flywheel, and that is supplied when the energy is required. So are you aware of this? Have you seen the flywheel by any chance? Yes or no? Everyone is aware? Have you seen the flywheel in internal combustion engines by any chance? It says that the literature says that flywheels have been used to store energy for thousands of years. That means a very, very old technology. They can have energy fade in the rotational mass, because thereby you can increase the rotational kinetic energy of a flywheel, store its kinetic energy and release out upon demand. So if you see the diagram of this particular flywheel, so this red color part represent the flywheel. Then there are magnetic bearings which are fitted here. The magnetic bearings, they reduce down the friction. Then this is the generator or motor unit. That means whenever the energy is required, that is taken out from the flywheel. Otherwise, the energy is stored in the flywheel in the form of increase in the kinetic energy. Then the power conditioning and external grid. So by any chance, can anyone tell me why this vacuum pump is required in this particular flywheel? Any idea why vacuum chamber is there?
Permeability?
No, sir. Any other guess? So this is the very, very important, and I will tell you the reason. The flywheel energy storage useful lifetime is more than 20 years. That means this is having the quite a long time. That means it can work for a very long time, and it is not having any kind of environmental concern. If you want to discard this, that means if you want to throw it, it is then out of function, then disposal is not a big issue as far as the environmental effect is concerned. For example, If the useful life of battery is over, then disposal of battery becomes a very, very problematic thing. Specifically lead acid batteries. Recycling is done, but not to the 100%. But that is not the case with the flywheel. So flywheel is basically a metal part. You can use it. There is nothing like which can wear out or which can get some damage. Flywheel you can reuse. Only the problem happens with the magnetic bearing here. Okay. Now this vacuum pump is used to take out the air because that will reduce the shear resistance to the motion of the flywheel. So it can increase the efficiency of the flywheel. If the air is inside this particular chamber where the flywheel rotates, then the air has got the viscosity and may offer the viscous resistance in which the energy can get dissipated or some amount of energy can get lost. So in order to reduce the viscous effects, viscous you can say resistances, the vacuum pump is used to take out some amount of air. So in addition, monitoring of the state of charge for FES is simple and reliable as only flywheel spinning speed is needed to monitor. So nothing much. But there is a disadvantage that the relatively poor energy density and larger standby losses. So the energy density is very, very poor. So it is used in only selective mechanisms and not the application is not very wide. So this is the energy storage system, basically flywheel based. So I thought of covering these two systems from the mechanical energy storages. Now we will shift to the other form of the storage system. Let me tell you that materials we are going to cover, but those will come in the latter part. And because I am not expert in the field of material science, so most of the time we will discuss the general aspects of the thermal storage system and how material can significantly improve the performance. Now these things we have discussed. Then the next slide is basically I'm talking about the thermodynamics aspect, which should be in continuous with the previous one. But anyway, because I missed the sequence of the slides, so it has come at the latter part. So we discussed the first law, we discussed the second law. Now there are certain shortcomings of this law we should understand. And the you know that the first law talks only about the conservation of energy. It doesn't tell us about the process, whether it is possible or not, then whether the process will happen in forward direction or it is a reversible process. It doesn't tell that. Then which type of process is this? That means whether it is a spontaneous process or non-spontaneous process. So it doesn't give any idea. It only says that if there is energy interaction, then before and after the energy will remain constant. That means this is not sufficient for us to analyze any kind of, you can say, storage system. For example, if you have this storage media, it can be liquid, it can be solid, it can be gas. If this is the storage media, you are supplying energy to it. Now if you want to use it, then this law, if you rely only based on this law only says that whatever energy is here, that means before entering, the same amount of energy has to be there. It only talks about the conservation. But if you want to take out the energy from this system, it won't tell you whether if acceptance receipt of energy is acceptable, where you can withdraw that energy or not, how much, that is not given. That is why we require to have the second law. So have you understood why we require the second law? Yes or no, sir?
Yes, sir.
So Without this, you cannot. That is why the second law is very, very important role to play as far as the energy system is concerned. So we'll see the second law and what are the advantages of having the second law to be in place is it gives you the idea whether the process is possible or not. Because if you try to find out gives free energy, it will give you whether this is possible or not. If you try to find out the entropy, it will give you the idea whether the given process, the Clausius inequality will tell you whether the given process is possible or not. Please understand that the the keyword for the first law is energy, whereas the keyword for the second law is, can anyone tell?
Entropy.
Yes, entropy. So entropy, how do you define that? The first law gave the concept of internal energy. That is why it is the law of conservation of energy, internal energy, whereas the second law gives the concept of the entropy. So that is basically the contribution. So can anyone define the entropy?
Degree of randomness.
Yeah, degree of randomness. Randomness of what?
Any thermodynamic cycle.
Yeah.
Sir, some of the participants are writing in chat box as well.
Okay.
One say randomness of molecules.
Yeah, definitely. It is basically chaotic situation at the molecular level. So that is basically the entropy. And as the temperature increases, the entropy is increasing. So having more entropy is going to create a problem, because if the system is not stabilized, it is in unstable range, then the dissipation of energy will be more. So the first law gives you the concept of energy, whereas second law gives you the concept of entropy. It gives the mechanism to quantify how much energy is generated and what is the state of the system. That means, see how it is important from the energy storage point of view is, suppose you want to store the energy, naturally you are going to add energy to that particular system. So the system entropy should not become very high, otherwise it will not be possible for us to extract the maximum amount of energy. So these laws, they have to be seen from that viewpoint rather than looking at only storage type of, you can say only storage media or the material. We should know these properties, that if I want to store certain amount of energy, for example solar energy, then the media in which I am going to store that solar energy, that media should not be in a state that you are not in a position to take it. So reversibility is basically the another factor. Okay. Then the direction of process, which we have seen that the first law it was not possible. In second law you can. Then the types of processes, you can say that whether the given process is spontaneous or non-spontaneous. Non-spontaneous process will require the external stimulus for making it start, but spontaneous process, they happen. For example, the water flows from, let us say, the high potential energy to low potential energy. The heat flows from high temperature to low temperature. These are the natural processes, they are spontaneous. Spontaneous not in terms of, let us say, the speed and spontaneity is not related. It is basically how the system, whether the given reaction will proceed or not, that is the spontaneity. So please do not get misled by the word spontaneous. So it is basically the possibility of the process to happen. So now important note is energy conversion or storage is also associated with loss of energy. That means every time you do this kind of things, this loss of energy is happening, and that is basically, sorry, sorry, one moment please. Are you able to see the screen?
Yes, sir.
Okay. So we need to see that the loss of energy will always be there, and this is basically causing the irreversibility. That means the process become irreversible, and believe me that the literature says that no process is reversible in nature. All the processes which are happening in the nature, they are irreversible. The moment we say irreversible, we say that if you store 100 joules of energy, the outcome will not be 100 joules, or there is a limit to the output depending upon the inherent property of the storage medium. That is why you can have the comparison of the different methods. So I hope the thermodynamic aspects, they are slightly clear in your mind. I'm not saying fully clear because the mathematical analysis we have not done it, but those who are not from mechanical engineering background, they might have got some idea regarding this. That means you can see the energy storage systems in light of the thermodynamics laws. Am I correct or not? Are these aspects helpful or not? How do you compare two energy storage media? Hello?
Participants, please respond to the. You can unmute yourself. We have not muted you.
Hello, sir.
Yeah.
According to charging discharging time and its stability.
Okay. No, that is correct. But see, what I mean to say that when we talk about the energy aspects, so my intention to give you this viewpoint is that every time you need to verify your systems on these two laws, uh, because if they violate, see, whatever statement you may make while designing, or while whatever assumptions you make while designing the energy storage system, you should always counter check that those systems should be logically tested on these two laws. That was my intention. You can have n number of systems, they are available, we can discuss, there are a lot of books available, research paper available, but examining those systems, if you go for the examination of any of the system, or if your student brings the system and if he claims something, then you should be in a position to verify it on the test of these two thermodynamics laws, and this will give you the clear cut idea. Okay.
Okay.
Yeah, so that was the intention. Now coming to the thermal energy storage systems, as the topic was given to me, so since I am from the thermal background, so I'll be more concerned about the thermal energy storage system. So usually the thermal energy storage system, they are the temporary storage thermal energy at high or low temperatures. That means uh, they can be used to meet the short-term requirements. Now, they are normally useful for correcting the mismatch between the supply and demand energy. That means if there is some discrepancy, they are not the sole system which will supply the energy, rather they will correct it most of the time. Okay. Now, the basic principle of thermal energy system is same. That means the basic principle of operation, it wants to say that you have the charging, then storing and discharging. This can be understood by a simple graph which will come in the subsequent slides. So first you charge the system, then you store for some time, the energy should be stored for some time, and then you discharge it. The same thing applies to the battery also. First we do the charging, then we use that battery wherever we require the energy. So now the low temperature, how do you classify this? There are many ways to classify this thermal energy system depending upon the time period for with the short duration, long duration and all those things. But broadly, people say that the low temperature thermal energy storage, they operate typically below 200 degrees centigrade. Generally building, heating and cooling, solar water boilers, then solar cooker. Most of these things, they are basically fall in the category of the domestic, you can say, uses. And high temperature is for industrial application. You can have the waste heat recovery. Usually this happens in the thermal power plant. The some of the waste which is coming out from the turbine, the steam is having certain amount of energy which you can use it by recovering the heat. uh, a small example of waste heat recovery is basically the example of a turbocharger in which is fitted in the internal combustion engines. Most of you are aware of the principle how the heat recovery is done in the turbocharger of the internal combustion engines. Yes or no? Then renewable energy system, basically the solar energy system. So the large scale application where the heat is more, those are the high temperature thermal energy storage, and where the heat is low temperature thermal energy storage. Now this will give you the idea, the conversion, and this is the you can say chart I have taken from one book which is mentioned in the reference, that the first is heat to heat. That means you want heat to get converted into heat, but you wanted to store it at some time. The example is waste heat recycling, storage for district heating. In standard thermal storage, heat is stored and later release heat. So these are the telling you that these are the ways that you can deposit one form of the energy, basically the heat, and in output either you get the power or you can get the heat. The second is heat to power. That means you store the heat and you get the power. So waste heat recovery, the examples is a steam engine is the best example, that you supply the heat, you get the power. It is stored, converted and then released as electricity. Then power to heat, electricity is converted into heat which is stored and later released as a heat. So such kind of examples are there. So this has summarized the energy interaction. That means you require in all these things, you require, you see that one thing is common, that is the thermal energy storage. So the next one is the power conversion to power. So domestic and district heat electrification. So this is a typical different example, but here you convert power in terms of the heat, and then heat getting converted into again the required, you can say, whatever a form of the energy you require. So these are general, you can say, the conversion and storages of the electricity, thermal energy. Now types of thermal energy storage. So if you have to design the thermal energy storage, then either it can be based on the sensible heat, then it can be based on the latent heat and the thermochemical heat storage. Now the major research is going on in this particular area, that is the thermochemical heat storage. Most of the systems, they are now shifting from these two to thermochemical heat storage. Basically the batteries and other things, they are of this type, hydrogen, that there are certain technologies. Now the as the name suggests, the sensible heat is without phase change. This is without phase change. That means if the storage media, there is no phase change. That means if it is, you are storing the energy in water. So water will remain water if it is the sensible energy storage. If it is latent energy storage, then you can have the mixed kind of phases. That means you can have the water, that is liquid, plus steam. And thermochemical is basically the you can have the component which you, when you supply the heat, the component then degrade or decompose into two components which you can separate, which you can separately store, and again you can use it back. So this is basically the difference between these storage, you can say, mechanism. So sensible heat, then latent heat, and thermochemical heat. You refer to any book on the energy storage. These are the first things which are discussed, and it is very, very easy to understand. For example, the if you take the example of the latent heat energy storage, then the phase change material is used, because the name itself suggests the solid gets converted into liquid and vice versa. So we'll see them one by one. We'll see them how to estimate the capacity of the thermal energy storage. So the thermal energy storage technologies are based on sensible, latent, alternatively upon reversible thermochemical reaction. The system based on sensible heat of material include hot and cold water tanks. Generally, these are the hot and cold water tank. It uses the word water. Nowhere it will mention the steam or vapor. The underground thermal energy storage, UTES, which is the short form which is used in most of the literature, or specific materials and structure wherein, uh, by the way, how do you calculate this sensible heat capacity? What do you mean by sensible heat? Which is the parameter which is important for this sensible heat?
Temperature, sir.
Okay. What else? Temperature is anyway, ma'am, it is important in all the three things. We'll see this. It is basically the specific heat capacity. The specific heat capacity, that is the CP. Uh,
Okay.
you must have studied CP and CV. The
Yes, sir. Yes, sir.
specific heat at constant pressure and specific heat at constant volume. So gases have two specific heats at constant pressure and constant volume, whereas liquids and solids, they have only one specific heat. And based on this, we can estimate. I have written the expression that I will tell you, the simple expression. Then the latent heat is basically uh, phase conversion. The temperature remains constant. Okay. The common example are the ice storage systems, which are utilized to relieve the peak air conditioning loads in the daytime hours in most of the countries. That if the heat is more, then you use the ice storage to absorb the heat so that your ice starts melting at the constant temperature. Then PCM based, usually now if we are discussing about the material, paraffins, esters, fatty acids, then salt hydrides, these are the materials which are developed to absorb or reject heat or narrow temperature band. And narrow temperature band meaning that you got to have the fixed temperature. During that, it will absorb the heat, and then again will start increasing the temperature. So as you can see that during winter days, the coconut oil will absorb the heat, will get solidifies because the temperature is going down. And once if you keep that bottle into the sunlight, it will absorb the heat. How the heat absorption takes place? Because it has got the specific heat capacity, the amount of heat required to raise the temperature of 1 kg of mass of the material through 1 degree centigrade. So that amount of it is known as the specific heat. which is at constant pressure if it is liquid. So that is basically the phase change material. Similarly, paraffins, they are also phase change material. You might have seen that when you light up the candle, the wax gets melted. So these are basically the paraffins which can exhibit such kind of property. Now, the broad classification, this I have taken from the book that I mentioned in the reference. So it's not created by me. So thermal energy storage, the physical heat storage, chemical heat storage, that will be separately discussed, which is not the purview of the present, you can say, presentation. So sensible heat is you can store it in solid or liquid, basically rock or metal. These are the things which are in use. I will give you the list of the materials which are used also in a tabular form. Then the liquid is basically thermal oil, molten salt, and water. They can be used as the medium for storing the heat. Now the latent heat, as you know that in sensible heat, the phase change is not allowed. In latent heat storage, the phase change is allowed. Basically, there are certain materials which absorb the heat and they change their phase. So there you can have the liquid to gas. That means during the absorption, the media is in liquid form and then getting converted into gaseous. For example, water to steam, then solid to liquid, then ice to water. That is basically the when during the you can say melting, the ice will absorb the heat, and solid to gas. So that is another thing, that solid to gas and solid to solid. So usually that is exhibited by polymers. So these are basically the materials. For example, organic phase change material, PCM stands for phase change material, alcohols, paraffins, ester. So these are the organic solids. Then inorganic solids, salts, metal alloy, metal compound, and eutectic PCM, organic to organic, inorganic, organic, and inorganic. So the list is most of the time available in the handbook of the energy storage material. So you can get it with the properties and everything. So for your particular kind of application where you want to store the heat, you can use it. For example, we use most of the time PCM when we wanted to cool the solar panel. So phase change material is most of the time people have tried it using in battery cooling as well, wherein it will absorb the heat when the battery is getting heated, and then it will dissipate the heat to the environment. Similarly, in the solar panel, suppose if the panel is there, if this is the solar panel, then the bottom side of the panel is having the phase change material, which is here. The phase change material, you can fill the bottom portion of the solar panel. When the solar radiation they fall on this particular solar panel, yeah, the temperature of the solar panel will increase, and if the temperature is increased, then the performance of the solar panel goes down. So this efficiency of conversion goes down. So in order to keep that, during daytime it will absorb the heat, and during night time it will dissipate heat to both, to the environment, and if there is no insulation here, the heat will also heat up the panel. So that is where the you can say skill lies of the designer, that how much amount of the PCM it wants to put it, and how it has to be dissipated. The heat has to be dissipated to environment, major portion, and not to the panel. So these are basically fall in the category of the latent heat storage. Is this clear?
Yes, sir.
Now, the amount, if you discuss the sensible heat storage, then the amount of heat stored is proportional to density, specific heat, volume, and variation of the temperature. Why I have made it in the red is that whenever you try to select this kind of storage, you need to consider the property of the storage media. The prominent properties are density, specific heat, volume. Generally, sensible storage system consists of storage medium, a container, commonly tank and inlet. The size is very big, an outlet device. Then it has given the type. Usually, if it is a solid media, then packed bed favor thermal stratification, that means gradation, and which has the advantage. That means you can take out the heat wherever you want. So working of sensible, it is basically how it works. Uh, by changing the temperature of the storage medium, typically water or rock, without a phase change. This I have explained you. They absorb heat when heated and release it when they cool down. The is They are basically cost effective because not much is required to be done for it. They are the passive kind of cooling system, or you can say storage is of passive kind. There is nothing like which you need to provide externally. Only if heat is coming, it will absorb. Now that is the passive type of you can say storage system. Now generally they require the larger volume. That is basically the compared to latent heat storage system. So that is, you can say, disadvantage as well. And sensible storage system have lower energy storage density compared to latent heat storage system. The storage density means it talks about the energy stored per unit mass of the media. This is a joule by kg. Energy stored, that is energy is in joule divided by kg. Sometimes they refer to as joule per volume also. That is again when you discuss it about the volume. So they also require large volume. That means this is more for these systems and this is lower for these kinds of systems. Significant amount of energy. So there will be certain advantages, disadvantages, they are associated with this. Then this is how the calculation is done. The amount of heat is integral Ti initial temperature to final temperature limit, mass of the medium, then the specific heat capacity and temperature difference. The major factor is this: if the Cp is more, the amount of heat which is stored, that is going to be more. Delta T, no doubt it is going to make the difference, but this will relate, this delta T is related to the speed of the process. If the delta T is more, then no doubt it is going to absorb the more amount of it. So that is also going to affect, but this will be according to Newton's law of cooling. So delta T is basically the absorption of this, but Cp value, it has to be inherently more. You might have heard that certain medium, they gets heated quickly and also they cool down quickly. So that is basically the effect of Cp. That means water takes more time to absorb the heat and also takes more time to lose the heat because it has got more value of the Cp, specific heat. Whereas if you mix water with ethylene glycol, the specific heat capacity reduces and then it will heat up also quickly and cool down also quickly the solution. So Cp plays a very, very major role. This is the simple expression to calculate how much amount of heat it has absorbed. Now latent heat storage. So in latent heat storage, the phase change is going to be there, and the latent heat is generally much higher compared to the sensible heat. So based on the phase changes, you can have usually the phase change materials: solid, 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 liquid, liquid, gas. So these are the solid liquids phase change is most suitable for many applications because it is compact. So this is the graph which this is the representative figure which shows that this is the sensible portion, then this is the latent heat portion, and again the sensible portion. If you correlate it water, you are in a better position to understand. Here there will be liquid, here there will be liquid plus vapor if you are considering the water, and here it is going to be the complete liquid, complete vapor. So this is basically storing of the energy in terms of the superheated steam. If you relate it with the water is also a phase change material, but it is not generally used for this thing. I'm just trying to give you the example for correlation. Usually solid to liquid will be used most of the time. So this graph will give you the idea. Then this is the complete cycle. The heat storage means full cycle. Previously, I have shown you only half cycle. Then this is basically the complete cycle. That means it's the during heating, during daytime it is going to get charged, and during night time it is going to get cooled. So energy storage, this is during daytime, and this is energy release during night time. So this is the complete cycle of charging and discharging. Now then the calculation can be done. It can be done for two phases. One is this is for the solid, and this is, if you see that there is a term which is called as AM, that is the fraction of phase change material that is melted. So these are the calculations, the simple calculations, and these are the calculations which are used in the ANSYS software for calculating how much fraction is melted and how much fraction is still remaining, if you are working on the analysis of the solar photovoltaic. Then advantages, so high energy density, reduced energy consumption, enhanced comfort and temperature stability. So now please see this chart. This may not be very clear if you are looking it on the mobile, but the phase change material, they are pretty old, 1910, then 1950 and 1990. The further I could not get it in the literature. So now right from the molten salt to now plastic crystal. So this is basically the changes. People are doing research in this particular area, and nowadays most of the thermal systems, they use the phase change material. Even for the recent example is lithium ion battery cooling is also you can say using the phase change material with the active cooling techniques. So phase change is going to be the you can say continuous getting upgraded. New synthesized materials, they are also being tried and verified. So those who are interested, they can get it in the literature, or whatever presentation I will share, you can refer to the reference section, so you can get that. So this is, then there is one interesting thing, that the energy storage duration. Because if you have to choose these kinds of technologies for the thermal storage, you need to be very clear. If you read this line, energy storage duration is primarily determined by commercial requirements. That means how long you want to use it, for what purpose you want to use it. And based on this, you will find that the 18 out of 20 thermal energy storage technologies favor to store energy for hours, which enables them to serve intraday to multi-day duration. So this is in hours. You'll find that this one and this second technology, that is also, that is not suitable. Rest all are suitable. Then 17 out of 20, 85% favor stores energy for days, ensuring multi-day duration. So only again 1, 2 and 3, these are the three technologies which are not favorable for storages of energy for the days. This chart is very important, or it gives a glance, at a glance, the technologies available and their duration. And then this is 5 out of 20 favor to store energy for weeks, some for months. So you can say the concrete, then steel, underground water, and water. These are basically they can store, and the chemical reaction storage. So they can be used for months. So this I could get it from one of the reports, and I thought of sharing with you. So this gives you the idea that if you have to use different kind of materials for storing the energy, which one is suitable and how long it can work. So I hope that this table is important from the point of view of, suppose you are working on any application and you want that the aging effect on the energy storage or thermal energy storage, then you can refer to this, because these technologies, they have been proved, researched, and the longevity or the life is verified. So from that viewpoint, this chart is important. Now technology readiness also, this is another important chart. Now you can make out this 7 to 9 include technologies up to proof in operational environment. You will see that. So what it says, 11 out of 20 technologies, these are the 20 technologies out of 20. This is quite a good number, more than 50%. Then 8 of them are in latter phases of R&D, where they are already proving themselves in the operational environment. And the last one is only one of them, 5%, is considered to be in the pilot phase. Now please see that these technology readiness, that means the remaining technologies, you can expect this is the one, the other liquid metals. So there is a lot of scope as far as the research is concerned in this particular area. So instead of doing lot of literature survey, if you refer to these two charts, you will come to know that where people are moving as far as the energy storage is concerned. Okay. Now thermochemical storage. This is most important part. The chemical storage technology is basically you got to have the thermochemical material to which you supply the heat, and then it will be broken down into two. These are the reaction. Then again, if you want to recover the heat, you reverse it. So that is why I have shown you this reversible arrow. So that is how it works. Looking at the time, I am hurriedly covering this. There is a lot of slides which we have to cover. So main process in thermochemical is charging, storing, and discharging. This is the common thing. The charging process is endothermic. Naturally, it is going to absorb the heat. The thermal energy is absorbed from this is endothermic process. That means heat is supplied to this. It is broken down into two components. Storing, after charging process, components A and B are separately stored with little or no energy loss. The materials are usually stored at the ambient temperature, leading to no thermal losses. And after storing, discharging, A and B are combined in an exothermic reaction. Energy can be transferred. That means this gets reversed. A plus B will give you C and the heat. Please note that the forward and reversible reactions, the forward reaction is endothermic, reversible is exothermic, but losses will be still there. You cannot do away with that losses. You can minimize that, but you cannot eliminate the losses. So this is the main concept behind the thermochemical reactions, which can be used as a storage, you can say, mechanism. Now people have found out that potential materials for thermochemical reaction is magnesium sulfate, silicon oxide, iron carbonate, iron hydroxide, calcium sulfate. So these chemical details are given: energy density, storage. This is gigajoules per meter cube. So these things are there. These are, please note that these things, they are in the research phase. They are not have been, they are the potential materials. The title says that. Okay. So I have read the paper in which they were saying that the people are doing research on this to find out. Then the remarks on the thermochemical energy storage is: thermochemical storage of higher energy density is relative to PCM. Can you please mute the mic? Then thermochemical energy storage technology is undergoing research and pilot test projects for assessing high storage density. That means this is the area wherein the potential lies. Now, sensible and latent, they are the most common and traditional techniques, but thermochemical, you have vast possibility. People from material, people from chemical engineering, they can, they may be much aware about this, but I have seen very few people from mechanical discipline who are working in this. The challenge is there are number of promising technologies and materials for the seasonal chemical storage of solar heat, but that much research remains before they become practical and economical. Right now, this is the difficulty or the challenge you face in case of thermochemical materials. So there is a good research area which is available. If someone wants to pursue his research, then can opt for these kinds of areas if if he or she is having interest in this. Now, the main area of research should be on materials which are either too expensive. Even if it is available, the challenges which the research paper mention is the materials are too expensive, do not have right properties, or have not been shown to work in prototypes with realistic boundary condition. So these are basically the challenges as far as the thermochemical energy storage materials are concerned. Now this chart gives you the summary of all the technology, the positive, negative points. So if you happen to get the time, please go through this, and this will give you the fair idea about these, the status of these technologies. Now with this, we will be concluding on the thermal storage. Now hydrogen based energy storage. Everyone knows that every now and then the newspaper, they say a lot of things about the hydrogen as a energy, because it is the one of the most efficient and cleanest and lightest fuels. Then it is found naturally and must be produced from primary energy sources, expected to play a major role in future energy systems. Like electricity, it must be produced and transported. This is possible. But electricity suffers one background. Electricity must be used that it is produced. It can be stored only if converted to other form, but that is not the case with the hydrogen. Hydrogen has one additional advantage over electricities. It can be stored, and this is the future lies in this world. It can be stored. If it can be stored in as it is form, then nothing like it. But you know that it comes with a lot of risk. So what are the potential risks that we will that we will discuss in brief shortly? The technologies for hydrogen store. Currently, the literature says that there are main four technologies for the hydrogen storage, out of which two are matured and two are still in the research phase. One is the hydrogen pressurization, and second is hydrogen adsorption in metal hydrides. So this is the very, very promising technology, metal hydrides. People are working on this. The remaining two technologies that are still in research and technological development phases are the adsorption of hydrogen on carbon nanofibers. Here comes the role of the nanomaterial, and liquefaction of the hydrogen. So we'll see this. hydrogen production, a representative figure. That means you can get the energy from the renewable sources. You you use the electrolysis technique to decompose the water into hydrogen and oxygen, store the hydrogen and use it as a fuel for the your application. You about 4% of hydrogen currently in use in the world is produced by electrolysis. So this is why, but electrolytic decomposition of water to produce hydrogen is currently quite expensive. That means getting hydrogen from the electrolysis is not very easy, or you can say it is a costly affair. An advantage of water electrolysis to produce hydrogen is that instead of requiring large central facilities, that means you don't have to have the large central facility, individual facility can be used and can be distributed. Distributed generation is possible in smaller units. They can be located at places near where the hydrogen will be used in order to reduce storage and transportation cost. But this comes with a disadvantages that the if you start producing or generating hydrogen at place, then it may be dangerous as well, because carrying hydrogen cylinder, if you met with an accident, then it can explode. So that is very, very dangerous. So you can store the hydrogen is basically a energy at a high pressure tanks. This is a common method at high pressure, but large volume of the tank is required. If you are using hydrogen in the vehicle, then the tank volume is not, you can say, small. Then storage of liquid hydrogen in insulated tanks, that is also a significant disadvantage in this approach, is that process of liquefaction requires 30 to 40% of the final energy content of the hydrogen. So losses are more in this case. Now the other method people have tried to find out is protons in solid, that is using metal hydrides. The approach is reversibly absorb hydrogen in solid metal hydrogen compounds called metal hydrides. That means there is a metal alloy LaNi5 to form LaNiH6. That means it can store 6 atoms of hydrogen. The capacities of such material depend on the amount of hydrogen that they can absorb in crystal structure. The storage of hydrogen in such material is very attractive from the volumetric standpoint. The demerit these metal hydrides is relatively small amount of hydrogen they can store per unit weight, and there is also some concern about the cost and large scale availability of some such materials. So that is the problem with this. These are the technologies which are in developing phase. Some of them are developed, but some of them are still in the nascent phase. So Prasanna sir, can I exceed for at least 5-10 minutes?
Yes, sir.
Okay. So with your permission, sir, I will just finish this thing.
Okay, sir. No
Yeah.
problem.
So storage of hydrogen, that is the metal hydrides. Then ammonia, that is another potential candidate. So ammonia, which is 17% hydrogen by weight. Now you can thermally decompose ammonia and can give you the hydrogen. So that is also another technology. And apart from that, you can have the other complex materials. It's not only ammonia. The other complex material, you convert it into ammonia, and again you break down the ammonia to get the hydrogen. So like metal amines, in which ammonia is coordinated to a metal ion, are one type of such material. For example, MgNH3C6 Cl2. So this is other complex material, because in order to reduce the, you can say, complexity, then you can try, instead of using the ammonia, you can generate ammonia and then decompose it. So that is the technology people are trying to use for generating the hydrogen. So reversible organic liquids are also used. For example, benzene, then toluene. So electrolytic production of hydrogen when electricity is readily available and inexpensive, and reacting it with a simple organic molecule to produce a product containing more hydrogen. That means you can store this. For example, you convert toluene into this particular compound, methyl cyclohexane, and then you break it down to get the hydrogen. So storage becomes easy. So 6 hydrogen atoms per molecule. Both of these liquids can readily be stored in large tanks, and then you can produce the, you can say, hydrogen. But problem is, you can use the hydrogen for the stationary energy sources, but if you have to use it on automobile, then it becomes very challenging, because all these organic compounds or any other complex compounds, if you mount it on the vehicle, and if there by chance there are collisions of the two vehicle, then it will act as a bomb. So that is another very you can say concern. And that is why you will find that though it is a cheap fuel, but that is not popular. You can use the hydrogen directly into internal combustion engine for getting the engine output. It is the cleanest fuel, no doubt about it. No pollutant, no pollution will happen, but again the risk is very high. Then safety aspect, if you see, hydrogen readily burns in air and with a flame that is almost colorless. So people have to be cautioned who work with the hydrogen open flame. So those working with hydrogen are always cautioned to keep it away from the flames. But no need to worry much. If there is a leakage, the ignition temperature of hydrogen in air is 585 at 1 atmospheric pressure. It's talking about the atmospheric room condition. Thus, there is no problem with having a mixture of these gases at ambient temperature, because it will not fall in the flammability limits. The density of hydrogen gas is very low compared to air, so it will always be getting accumulated, collected at the roof of the room if it is closed space. This reduces the possibility of reaching the flammability compositional range in open spaces. In enclosed spaces, hydrogen tends to accumulate at the highest location, that is near the ceiling rooms. So in any case, it was contended that any hydrogen that got free would rise so rapidly that its possible combustion would not be a threat. Only in case of the impact load, the hydrogen is dangerous. So this is regarding the hydrogen storage. And looking at the time constraint, I would like to stop here. I'll just go through the remaining slides. Basically, storage of electrical energy, then simplified lithium-ion battery. This was the topic which I was planning to discuss, and at last the introduction to supercapacitors. One more interesting thing is, this is basically the chart. I could get it from the literature. This will give you the available energy storage technologies with the capacities on this, and the charge and discharge time on the x-axis. So if you happen to get the time, you can go through this for your reference. So the future of energy storage is basically the batteries, which I could able to get it, and the nanomaterials for reducing the size of the storage media, then using nanomaterials for storing the energy, because with nanotechnology you can synthesize the material, can make the properties whatever required for making the energy storage medium. So these are certain references which I referred for making this particular presentation. So I tried my best to share with you whatever I could able to gather through these literature, because I'm not the person who is directly working on these kinds of technologies. Rather, we use this technology for our own purpose meaning for the cooling purpose rather than energy storing purpose. So with this, I thank you for listening my presentation. If listening to my presentation, so if there are any questions, then I will try my best to answer the questions. So over from my side, over to you, Prasanna sir.
Thank you, sir. Dear participants, if you have any question, then please unmute yourself and you can ask.
So sorry, I exceeded the time just by 5-10 minutes
Nice, sir.
because I have given the presentation on the energy storage material for the first time. Usually we are very habitual for giving the presentation related to the heat transfer and the automobile.
Oh, sorry, participants. Now I have changed the setting. Now you can unmute yourself.
Yes. Thank you very much, sir, for your guidance related to energy storage material. My one question is, uh, in case of energy storage, one person also see the temperature, the range of temperature. Means generally, like for part of the different materials, and by doing SEM, XRD, and then we suggest some suitable material for a specific application. Like this, can we start doing, like as you said, specific heat capacity, temperature range, and suggesting material for specific industrial application? So your thoughts or your guidance in this regard?
So actually, material from material point of view, uh, there are certain tests which can be done, but the main properties of that material is it should able to retain the heat with the minimum amount of losses. And to find out such kind of material and its applicability, you have to work on the thermodynamic aspects of that particular material based on the certain basic properties, for example density, thermal conductivity, then the viscosity of that particular material if you are dealing with the you can say material which can flow. So right now I can't suggest you anything from the point of view of the material science, you can say per se, but from mechanical point of view, it is basically the amount of the thermal, you can say hysteresis of that material is very, very important. So we need to study that. And see, we have also observed that in one of our application, we were cooling the solar panel. Found out that capacity for some material that changes over the